Yeah, go for it.
We are complete. Okay, so it's my great pleasure to welcome you to 591D and also to the Northwest Database Society series of talks. And today we have Laurel Orr. Laurel has spent 1.5 years as a postdoc at Stanford. Before that, he was in our group working with Magda and myself. And she's going to talk to us about what she did in this one year and a half at Stanford. So Laurel, take it away.
Awesome, thanks, Dan. Yeah, it's been a very crazy first year, and I'm very excited to talk about some of the work that I've been doing over there, and a little bit of the stuff that I've been thinking of right now, and sort of ongoing work in our lab and stuff that I've been doing. And so this, I'm going to be talking about a lot of my talks going to be on this system called Bootleg, and I can tell you the story about the name later. And this is our system for entity disambiguation. And this was also a work presented at CIDR this last year. And I'm going to talk about the system, but also sort of tie in pieces of what the system means for like data management as a whole, and sort of where I think sort of some of the interesting questions are for future research. And so I'm just going to sort of go up front and be like, here are the main points that I really want you guys to take away from this talk. So I remember for most talks, you really pay attention to the beginning and then potentially not so much at the end. So if there's one slide to pay attention to, it should be this one. And this is very much my biased view of the world. But as I see it, industrial pipelines are increasingly using embeddings to share and transfer information between tasks and products. And there was even the keynote this year at Pods was talking about embeddings, I mean, more from the theoretical side of things, but they were certainly sort of drawing a lot of attention. And my sort of view is that managing and maintaining these embeddings and the downstream systems that use them is really a fundamental data management problem. And they really sort of need our help in helping sort of managing these systems. And in this talk, I'm going to give two sort of use cases of how the data management sort of fits into this pipeline. And one of them is going to be about how to actually build high quality embeddings using notions from structured data. And that's talking about our system Bootleg. And then I'm going to talk about some ongoing work, which is how you can actually correct for embedding errors through data management techniques. So I'm just going to motivate this sort of ecosystem with a very sort of simple example. So suppose you have some sort of QA system, right? And the goal is you ask some sort of natural language query and it gives you some answer. So if you said, how tall is Lincoln, which apparently is actually a very common query, the answer would be expected to be 6'4". Now, for some people, basically like my parents, for example, this is very magical. They have no idea how this works. But I actually want to take one step deeper to understand what happens actually in between the query and actually the inputs into the QA model. So given a query, the actual core pre-processing step that needs to happen is where embedding representations are generated for the different inputs. So the words, for example, are going to get turned into different word embeddings through some sort of either static pre-trained word embedding or a contextualized language model. And then the entities are first going to be disambiguated, which I'll talk about later, and then also turn into sort of their embedded forms as well. Now, the key thing to understand about this is that these pre-trained embeddings are trained to sort of incorporate global knowledge about what this object is. So a word embedding is going to encode, for example, co-occurrences of different phrases so that the word tall in the embedding space is going to be very similar to a word like height. On the entity embedding level, the embeddings are going to code facts about what that entity is. So the Abraham Lincoln embedding is going to code information that he was, the former president of the United States, or that he is 6'4". And so the key thing here is that these embeddings are really critical inputs to these downstream systems, because then they can actually leverage the sort of factual knowledge encoded in these embeddings to perform their task. And these embeddings have provided lift across numerous tasks, including QA, where it could sort of use this fact that Abraham Lincoln is 6'4" to answer your question. So these embeddings don't exist in isolation. It's not as if you have one set of embeddings for one system. There's actually an ecosystem, and especially in an industry, that's forming around these embeddings, where the same embedding is being shared across multiple downstream systems. And these embeddings don't just sort of appear out of nowhere. They're also trained, typically over massive corpuses of data. And so this is what I'm calling the embedding ecosystem. There's the training data, the embeddings themselves, and then the downstream systems that leverage these embeddings. And at each step of this ecosystem are really unique challenges that are still open and I think need to be solved. On the training data side, you need to be able to sort of manage and integrate these structured and unstructured data sources in order to better train these embeddings. On the embedding side, you need to be able to understand how to build high quality embeddings and how to search over embeddings and monitor and version them. And on the downstream product side, you have to be able to understand the errors that are occurring in the model and how to patch them. If you go back to our sort of QA example, if the underlying entity embedding was actually incorrectly disambiguated to Lincoln, Nebraska, rather than Abraham Lincoln, that's going to make the downstream QA system struggle to answer struggle to get the right answer. So the takeaway here is that the same embeddings are being used across multiple downstream products. And this is a really sort of new, exciting world in terms of how do you actually manage this end-to-end pipeline.
So I have a question, Laurel.
Yeah, Magda.
So you can also, you can kind of create embeddings for kind of all these tasks so they can share those embeddings. And for some maybe domains like, word embeddings, because they have kind of their own meaning, or I think entity embeddings, this works really well. But for other examples, it might be that embeddings that are a little bit more specific to the task at hand might be better. So what is your take on like the use of general embeddings that are really shared across all the tasks versus more task-specific embeddings?
Yeah, no, I totally agree. That's actually really we have some people actually working on this question. We call them more like personalized embeddings, like personalized models, kind of. And there's sort of, in my mind, a couple different layers. For one, there's like global knowledge, like global embeddings that are like across the world, like Wikidata embeddings. Then there are like product specific embeddings. Like if you're at Amazon, maybe each user is going to have their own embedding. And then maybe even on a more personal level, if you have maybe your own personal contacts, maybe that would get its own form of entity embedding. And I think clearly there needs to be some way of sort of training and learning these sort of personal embeddings. And I think some of the really interesting questions there is actually how to sort of integrate knowledges from all layers. And so we don't necessarily just want to have personal embeddings, because there are sometimes, when you're asking Siri, like, this is an odd question, but like, did my dad go to Walmart today? Which is odd that you're asking that about your father, but suppose you did. In that case, that's a really nice question that's actually integrating global knowledge with personal knowledge, right? Because your dad is your dad, but Walmart's like this global entity. And so I think that's what sort of the interesting questions are in that space. And there's still, in my mind, a lot of interesting work to be done there in terms of how to train those and integrate them.
And a really quick question, also sorry for being late, I had a childcare issue due to a COVID thing. Well, I don't want to derail, so maybe I'll get to this, but like, how does this intersect with the classic kind of, federated learning type setting where you have, the classic example is you have a local model on like a phone, a user's phone that has some model of, their contact list, and then you have a global shared model. Federated learning, I guess, is kind of focusing on that aspect in the, nowadays often in the privacy, from the privacy perspective, but it is also, classically about this trade-off between like local model and global model. I don't know if there's like any thoughts on how this stuff. That's kind of that's an overly broad question, but I'll just turn it into a note instead. It seems like there are some interesting overlaps there.
Yeah, no, absolutely. And we have a student who's sort of working on this notion, especially in the form of privacy. And I think for her, it's some of the questions that we've been thinking of is, particularly in terms of training, you want to be ideally to really be sort of privacy preserving. You'd like everything to be done on your local device for the sort of personalized part of it. And so there's some questions that she's trying to answer, which is how do you sort of better train that kind of model so that you don't that you're able to best sort of incorporate this model and not sort of forget anything from the global knowledge and be able to sort of integrate it correctly. So yeah, no, I agree that there's a lot of interesting questions in that space as well. So
that's like the classic, federated learning setting. And so I guess, maybe federated learning meets modern embedding methods is like the interesting area here.
Yeah.
High level. Also, hi, Laurel.
Hi. All right. Yeah. Great questions. All right. Okay. So in this talk, I'm going to sort of focus on two of these problems. One of them is, as I sort of mentioned earlier, which is how do you think about building a higher quality embedding? And in particular, we're going to be focusing on entity embeddings and these more global entity embeddings, not so much personal ones here. And this is with our system Bootleg, and I'm going to talk about that first. And then I'm going to talk about some ongoing, very ongoing sort of preliminary work in how do you sort of fix errors through the embedding themselves through sort of data management techniques. And so the first talk is obviously going to be about this sort of entity embedding system that we're calling Bootleg. And this again was the work that was presented at CIDR this year. And so just to sort of give a primer as explicitly what I mean by entity disambiguation is this is the process, as we like to say, that's mapping from strings to things in a knowledge base. And again, this is a global knowledge base here. So again, if you're asking your question, if you're asking a personal assistant and how tall is Lincoln, this is actually referring to Abraham Lincoln and not the sort of car company or the location. And this process, as I sort of highlighted earlier, is a key part of downstream systems like personal assistance, search, and information extraction that are sort of used by millions of users every day. Now, these entities lie on a spectrum of popularity, which we sort of think of in terms of four groups. The most popular entities are what we call head entities. And these are ones that appear very frequently in the training data. So like Washington, D.C. or Abraham Lincoln is a fairly popular entity. And there's a lot of textual data associated with these entities, meaning that sort of existing information retrieval methods or sort of language model based baseline NED systems are going to do really well because just by memorizing sort of textual cues, you're going to be able to disambiguate these entities. Now, these are followed by sort of torso entities, and these are sort of terms that I've created here that are sort of less frequent than head entities. And then on the other end of the spectrum, we have what we're calling tail and unseen entities, which I sometimes call toe entities, just to sort of fit in line with the body part theme here. And these are those that appear very infrequently or not at all in training data. So for example, this song Sauce by this artist, which I'm not even going to try to pronounce, doesn't even have an associated Wikidata ID associated with this song, yet people are still going to ask their personal assistants to play this song. And so it's really critical that we're able to sort of understand how to disambiguate these rare entities. And importantly, even though they're very rare in sort of standard training data sets, the majority of entities that are seen by these systems, and in general, the majority of entities are these rare ones. Only 13% of entities in Wikidata have a Wikipedia page with textual information. And only 1% of songs in all of MusicBrainz, which is a music database system, even appear in Wikidata to begin with. So the tail kind of constitutes a huge portion of sort of queries seen by these systems. Now you're left with a natural question, which is like, well, what if the simplest solution would just be to scale up our training data? Let's mine for more data and try to sort of learn these, learn to understand the tail via by increasing the size of the data. Now, the problem with this is that the large number of patterns that are needed to resolve the tail make this actually very difficult to scale. So here we have a plot, which is saying, looking at the popularity of an entity in training data versus the F1 accuracy. And this is looking at our system Bootleg, which I'll talk about later, versus a baseline model that actually used a language model named BERT in order to perform disambiguation. And so this baseline model just had textual cues. And what we see here is that for the head, the popular entities, the models perform very similarly. It's only when we start getting to the rare entities that we start seeing a performance difference. And so in this case, for example, if you wanted an accuracy of about approximately 60 F1 points, this baseline model has to see an entity on the order of 100 times during training data, or during training. Now, there are approximately 90 million entities in Wikidata. This would mean that you would need about 90 times the 100 million training examples in order to sort of hopefully get 60 F1 points across all these entities, which just presents a sort of huge scalability challenge. And so what I'm going to talk about with our system Bootleg is how we actually leverage subtle reasoning cues, which I'll talk about later, to sort of better understand the tail and better disambiguate the tail. And this is going to improve performance, as we show, by up to 40 points on these rare entities. So just to recap, there's two key challenges here that we're really trying to address with our system Bootleg. The first, as I talked about, is this rare entity problem. The majority of entities are rare, and it's very difficult to scale a model in order to be able to solve them, to disambiguate them. So you're going to have to actually leverage subtle reasoning patterns and sort of structured information in order to disambiguate them. Now, another challenge, especially when you're dealing with industrial NED systems, is how to have what I'm calling hands-free engineering. And this is where hand-labeled data and hand-curated features is very difficult in terms of maintaining and scaling a model. If you, for example, wanted to build an NED system across multiple languages, you'd have to go through and relabel each of those data sources, which is very expensive and time-consuming. And so our take on this is that you have to build a model that's what we're calling self-supervised, that does not use any hand-labeled data or sort of hand-curated features. It has to be something that's, in essence, what we're calling hands-free. And this makes it much more easy to extend and maintain in an industrial setting. So for the first, so to answer the first question of how you disambiguate over the tail, I'm going to show you how what really matters here is actually the incorporation of structured information, in particular information over types and relationships. Okay, so before I sort of get into the structured knowledge, I'm going to give you a little bit of a primer as to how NED systems work under the hood. So given an input sentence, like the sentence, where is Lincoln in Logan County, the output needs to be sort of the entities that participate in that text. So the first step to this is what we're calling candidate generation, or is where you extract possible candidates. So here, Lincoln would have candidates like Lincoln, Illinois, or Lincoln, Nebraska. And Logan County would have candidates like the Logan County in Illinois, or the one in Ohio or Oklahoma. So the first step to this is actually going to be what we're calling entity profile extraction, where you sort of query a database and get information about the entity. This includes its identifier, its title, and sort of any metadata or structural information you have about it. This profile information gets turned into what we're calling an entity payload, which gets fed into our neural model, which is going to output the right answers. Okay, so now we're ready to dive into these sort of subtle reasoning cues that I hinted at earlier. So disambiguation, as I'm going to show, requires learning information about individual entities, relationships, and types. So I'm going to unpack that statement with a couple of examples. So if I asked you, where is Lincoln in Nebraska, or what year did Steven Spielberg make Lincoln, you'd be able to know that the first refers to Lincoln, Nebraska, the city, and then the latter to the movie, as words like Nebraska and Steven Spielberg commonly co-occur with each entity. And these are sort of textual patterns. Now, the problem is that these patterns are associated on the entity level, meaning they don't generalize to other entities. In particular, rare entities that aren't seen during training are not going to be able to be resolved by these entity-based memorization patterns because they're not going to be seen at all during training. So the next signal is what I'm calling knowledge graph relations. So if you have the sentence, David and Victoria Mitchell added spice to their marriage, in this case, you have that David Mitchell is going to, or excuse me, in this case, there are actually two Victoria Mitchells in Wikipedia. One of them is a poker player and one of them is a runner. Only one of them is married to a David. So the only way you know which Victoria and David is correct is by using information about the relationships between entities. Now, importantly, these relationships can transfer and generalize to rare entities. If I know what it means to be a married couple over popular entities, that knowledge can actually transfer to married people that are rare entities instead. So this is a type of signal that does help us generalize to the tail. Now, the last signal that I'm going to talk about are type patterns. And here we see that types also have sort of textual cues associated with them. So when I have the question, how tall is Lincoln? That's using the fact that people have heights, not car companies or locations. What is the cheapest Lincoln is referred to the car company, not the person. And how many people are in Lincoln is a question that's related to locations, not people or car companies. And again, this is another pattern that generalizes to the unseen entities and rare entities. If I know what it means to be a person, that information can transfer to rare entities, to rare people as well. So as we just saw, there are these three different patterns that have sort of different generalization capabilities, with text patterns being the least general because they're at the entity level. So to motivate the rest of the hierarchy between KG relationships and types, we took a very simple analysis of Wikipedia and found that 22% of entities have a relationship, and 126 of these relationships occur more than 100 times. This indicates that we are going to be capable of learning patterns at the relation level and allow those patterns to sort of help us generalize to the tail. Now, as more entities, as 96% of entities have types, we're going to actually make that a more general signal and sort of put that at the top of our hierarchy. So the key takeaway from these last sort of set of slides here is that by learning patterns over types and relationships, we're going to be able to better generalize to the tail. And so the next natural question is that how do you actually encode this information into a model itself. And I'm going to show, sorry, and I'm going to show you how we're actually going to do this all through the notion of embeddings.
And I guess the,
yeah, go ahead.
Oh, sorry, just to understand, I guess the prompt is, if you're just saying, okay, learn these different types of signals or features, that would, be a kind of vanilla, prompt for, training a model, but it's how do you train them when globally they're so disproportionately represented that if you just had a, standard training procedure, you would put all the weight on the kind of text memorization features.
Yeah. No, and that, yeah, absolutely. That's something that I don't talk about the details in this talk, but there is, let me go, can I go back? Yeah.
I mean,
so
you're motivated well.
There's actually a really sort of fundamentally question here, which is when you're giving a model different pieces of hierarchical knowledge, how do you actually help it learn at the right level? Because naturally, you're right, a model is going to actually absolutely go straight for the memorization cues. And if you don't sort of encourage it otherwise, it's not going to learn as much over the types and the KG relationships. And so there's also some interesting notions in terms of how do you regularize models to also encourage it learning the sort of more general patterns as well, which is something that we mentioned a little bit in the paper, but not in this talk as much. Right. Okay. So here we are back to our sort of high level diagram. And I'm really going to focus in on this sort of piece here, which is the payload in the neural model, to explain to you how we use embeddings to sort of learn signals at each layer of the hierarchy here. I'm going to break down what happens for a single candidate. So take the Logan County, Illinois, and the profile generated from that. So we're going to first use this to extract entities, and extract embeddings, and we're going to have an embedding, importantly, for each level of the hierarchy, the text memorization, types, and relationships. So what this means is that first, I'm going to use the unique identifier of that entity to generate an embedding that is unique per entity. And this embedding is going to store sort of entity unique textual features, mainly textual features. I'm then going to use the notion of relations to extract relation embeddings, one for capital of and maybe one for named after. And the important part here is that every single time the relationship of capital of appears, it's going to get the same embedding. I'm going to repeat the process now for types as well. So we're going to have a county type as well as a sort of geographical location type. And the fact that, again, these types and relationships are shared across all entities is what's going to allow the information to sort of transfer across entities, because maybe a rare entity comes along that was not seen before. Its entity embedding is basically going to be random, but it's still going to get useful signals from that type embedding. These all simply just get projected down into what we're calling our entity payload or entity representation. And again, the key part here is that this payload now is incorporating patterns at each level of this hierarchy. And so this payload information is sent into our neural model. And I want to highlight here, this is not a fancy model. This is not complex architecture. We tried to keep it as simple as possible while allowing us to still encode this information. And so we use sort of this omnipresent transformer module. We sort of stack them together and have it learn sort of patterns across these sort of learned representations, as well as by feeding it into sentence. And so more details are going to appear in sort of an upcoming machine learning paper, but the high level takeaway here is that we chose a very simple architecture that just allows us to sort of learn patterns between the sentence itself and all of the entity representations in the sentence to output the most likely candidate. Okay, so we just saw how to sort of generate our payload information and our neural model, and now I'm going to kind of cover a question that I hinted at earlier, which is how do you actually sort of train these models in a self-supervised fashion? And the answer I'm going to say is that, I mean, this is somewhat standard for entity disambiguation system, but it's still a very important point to highlight, which is that we're going to do it simply by, in quote marks, reading Wikipedia. And so this is, again, the important part here is that I'm really trying to motivate that we're able to sort of self-supervised methods for training this model that do not require any hand-labeled data here. And so luckily for us, we have existing sort of knowledge sources and textual information that we can leverage for training. And this is also going back to sort of the sort of personal model point. This is another really interesting challenge, which is how do you actually train personal models over data that isn't as sort of omnipresent as Wikidata and Wikipedia. So Wikidata gives us the structural information over types and relationships, while Wikipedia is going to give us sort of the textual information and, importantly, the sort of labels that we're going to be able to generate here. And so for Wikipedia, you can have these like interlinks in between Wikipedia pages that actually give us the links and the labels for us to train together, for us to train off of. So in the sentence, although they toured together, Lincoln did not take its name from They Might Be Giants' album Lincoln. In that case, the Lincoln on that page is actually pointing to Lincoln the band. And so we can actually use this as a training label for us to train our model. And the important part here is that, again, this did not require any manual labels. And it's much easier to extend this to other languages because you can simply sort of download a new version of Wikipedia. There are some interesting challenges in terms of how some languages have less data associated with them, but that's sort of a future problem. Now, one thing I want to note here is that Wikipedia is not perfect. And in particular, if you notice, this second mention for Lincoln was not highlighted. And that's sort of an artifact of Wikipedia itself and how sentences are typically labeled by users. But this is problematic for us because this is actually a missed mention that really should be labeled to the album for Lincoln. And so in our system, what we actually do is we apply a sort of weak supervision, weak labeling basic technique to go through and sort of heuristically label these mentions. And so in this case, we would have labeled the mention Lincoln to be pointing to Lincoln the album. And this is sort of a very simple sort of standard sort of weak supervision method that adds sort of about 1.7 times amount of training data and improves performance over the unseen entities by about 2 F1 points. And the important part here was I'm sort of hinting at the fact that actually simply through some data engineering techniques like weak labeling or weak supervision, we're actually able to sort of modify and impact performance of the model. I'm going to come back to that point later. So now I'm going to give you some very quick sort of experimental results for the system Bootleg that's sort of showing that it's a state-of-the-art model, but also is able to provide significant lift over the tail compared to sort of standard baselines and on sort of downstream production tasks here. And so this is sort of, if you're familiar with any sort of entity disambiguation benchmarks, this is sort of showing that our model does well on sort of standard benchmarks. I'm gonna be honest, this isn't actually that interesting. The tail performance is really what matters, is really what we're after here, because that's the core problem that's faced with sort of these industrial workloads. And so here we're comparing Bootleg on a Wikipedia data set to a simple language model based baseline. And you can see here that over all entities, we're about 5 points away. And I'm going to be very honest, we didn't really tune either of these models. And so I'm sure with some extra tuning and sort of we could have sort of increased the performance and closed that gap even more. 5 points isn't a lot in my mind. It's really over the tail and the unseen entities that you see a dramatic change in performance, where Bootleg sort of 40 points or more higher on these unseen entities. And this is something that you can't recover from tuning. And another really subtle point, which is something some other research going on actively in our lab, is that overall F1 metrics are really misleading, right? The all metric here, which is also a very standard sort of uniform data set, does not sort of give you the fine-grained evaluation that you need to really understand these models. And now we also sort of included Bootleg embeddings into an overtime production task at Apple, answering sort of factoid queries. And here there's sort of relative lift performance, relative lift metrics here. And we see about an 8 to 17 lift in production tasks, even over multiple languages. All right, so are there any questions? I want to take a pause here.
So I have a question. So you just mentioned that the F1 metric is too coarse-grained to evaluate these systems. So what are the alternative? Do you have an alternative metrics? Yeah,
so it's less about the metric itself and more about the fact that this is it's overall sort of uniform subset of data. And so a very sort of interesting thrust in our lab is understanding how to sort of look at relevant subsets of data that are potentially smaller, but more important for understanding model performance. And how this is really what matters in terms of understanding the sort of semantic performance, is looking at sort of subsets of data and not simply uniform metrics, which are very common, especially across benchmarks. Like most people just report uniform metrics. And so the point here was more, you really need to also the ability to incorporate some notion of domain knowledge in terms of understanding what subsets of data matter for overall performance. Okay, so I just sort of talked sort of at a high level about our sort of Bootleg system, which go ahead.
Oh, sorry, really quickly.
Yeah.
So going back to this original, so I guess the model you have essentially I guess in pre-embeddings times, correct me if I'm wrong, or back for Chris in the deep dive days, I guess we'd call this a special type of weight tying between the input features. So they're essentially like they're tied or they're uniform across all of certain features are tied across everything that has the same type. Certain ones are tied. It's the same thing of just sharing and embedding.
Right.
So there you have this model that you're training to do entity disambiguation.
Right.
But those resulting embeddings, I guess, just going back to the initial slide, it looked like the overall goal was to use the embeddings and produce the embeddings. Like, are you trying to use those embeddings for things other than just this model you're training?
Yeah.
Is that
So
part of the objective or the metric that you evaluate on?
Yes, and yeah. So a couple. Yeah, so for this sort of simple NED task, it was just looking at sort of entity disambiguation itself. I should have actually put these results on the slide. We did also, I mean, in my mind, the NED system is only useful in as much as it should be, as it's used for downstream tasks. And so we do also have experiments in sort of an upcoming paper that's looking at using the output embeddings, which are basically the output payload information from the model into downstream. We look at like a relation extraction task, mainly the TAC-RED task. And so we're able to show there that our embeddings are able to sort of boost performance on sort of so we took a baseline relation extraction model, added our entity embeddings to it, and then we're able to find sort of that there was a lift in performance, particularly because the embeddings, the bootleg embeddings, were able to sort of encode relevant information about the entity into the model, into the embedding that was then transferred to the TAC-RED model. So yeah, we were able, so these embeddings were used downstream sort of successfully. And this is still something that we're actively looking at as other tasks as well. And sort of extending and understanding when embeddings provide lift versus when they don't, because I don't think all tasks are actually going to benefit from these kinds of embeddings. It sort of just depends on the task itself.
I guess would the guess be that because in the entity disambiguation setting, you have entities that have many different types and relations, that any downstream task that is about classifying types or relations could potentially benefit?
Yeah, so it's also that, I mean, we also have the sort of there's some existing work that's showing that even if you're looking at like a simple language model embedding itself, that like the facts encoded there, like that Lincoln is 6'4", will be useful itself. So yeah, there's that notion, and also the notion that, so there's three things in my head here. There's one, which is like standard entity embeddings are going to help, whether or not they're sort of text-based only or incorporate the structural information. Then there's a caveat to that, which is they're not going to probably help over rare entities. And so to sort of improve performance over the rare entities, you have to have sort of better entity embedding itself. So that's sort of one piece. And then the other one was that, yes, anything related to types and relationships should help. And we also have some experiments that were never published, but that we're looking at actually just using our type embeddings rather than the actual entire sort of output embedding, and also showing that sort of provided lift. The notion that just really having some type information can help.
That's super cool.
Yeah, I think it was just types, or it was like only a model of ours trained on types. Somehow it was only related to types. There's another, I have to recall from the student what the experiment was. Yeah, and we're hoping to, I mean, it's interesting to have these different these different embeddings as well. I would love to sort of do more work understanding exactly what they encode, which is sort of interesting. All right. Okay. I just realized that's blue background. Okay, so I just sort of again talked about this sort of our sort of entity disambiguation system, Bootleg, and how you can incorporate structured information to sort of improve quality over embeddings. And this is also something I want to highlight here is although we focus it a lot on entity embeddings, there's also some interesting threads here about how can this high level idea of incorporating structured knowledge help with other sort of embedding methods as well. And there's a little work in our lab that's like trying to understand, I think, how type embeddings or type information, I'll say broadly, with like a standard language model can help. Right? So there's lots of interesting questions about how do you better generalize to the tail in general with these embedding systems. But now I'm going to talk about this sort of next problem that's very ongoing preliminary work, which is how do you sort of fix embeddings when errors arise on downstream systems? And so to motivate this, let's kind of go back to that simple QA model that I presented before. So suppose here an engineer is sort of looking at model outputs and is noticing that the QA system is missing a lot of queries related to national sports teams. And this is an error that I see all the time actually in our disambiguation models. And so upon further investigation, the engineer notices that the sort of underlying NAD system like Bootleg is mispredicting, miscorrectly is not a word, mispredicting national sports teams mentions like the word England for mispredicting them as a country rather than a sports team. So in this sentence, when did England last win the FIFA World Cup? A country itself doesn't win the World Cup, the soccer team does. But our model is actually mispredicting that as the country rather than the sports team. Now, this is problematic because it's going to be hurting not only this sort of QA system in this example, but as these embeddings are the ones that are shared across all these downstream products, this error is going to be impacting performance sort of across all of them as well, right? So it's not just an error. It's not necessarily going to be an error isolated to one system. It's going to be appearing across multiple different systems. And so we're left with a question, which is, well, how do I fix this error? You know, if you're in production, you have to be able to patch errors. And so one sort of solution would be, well, why don't I just fix up the QA model? You know, there's existing techniques, which I'll actually talk about next, of how to patch models. So why don't I just go patch the QA model itself? Now, the fundamental problem with that approach is that it's going to lead to inconsistencies across products. So that as a user, when you interact with Siri, for example, you maybe get different performance or different sort of answers than when interacting with some other Apple product. And from a company's perspective, this is really problematic because you're going to get, again, inconsistent performance. And so the solution that we're arguing is that these errors actually need to be patched, assuming they can be, in the underlying embeddings themselves. And not only is this going to help maintain product consistency, but it's also sort of an efficient method for patching errors, because you patch the error in the embedding, the error basically gets propagated for free to all downstream systems. And there are some interesting questions involved that we're still sort of asking, which is, if you patch an embedding, how do you sort of best update the downstream model? But assuming that that's sort of solved for you, this is sort of the high level principle, is if you patch the embedding, you're going to fix all of the downstream models, or at least with respect to that error. So now we're left with a question of, how do you actually go about fixing models, and what methods are we going to take to do so? And so I'm sort of simplifying this problem a lot, but at a high level, there are some sort of two core camps that I see in terms of how do you fix models. One of them is sort of standard, what I'm calling model engineering techniques. And these are where an engineer would go in and maybe do feature engineering, modify the training regime, fix the model architecture to sort of improve the model or fix an error that the model is making. Now, the problem with this I see is that it's going to be hard to maintain this, as you're basically going to be building custom models for every single downstream task. And this also is going to require sort of engineer expertise to be able to sort of modify the model itself. And a much more sort of sustainable way is on the right side, which is what I'm calling data engineering techniques. And these are some methods, which I'll go into a little bit more detail next, that are sort of tried and true techniques like augmentation or weeks revision, or also sort of a slice-based learning method. And the core thing I want to highlight here is that by modifying the data itself, not only are you kind of giving a data set that potentially other models could use, or other sort of embedding methods, but fundamentally you're keeping these models sort of black box commodities that you don't have to touch or engineer, right? So just by changing the training data, you're gonna be able to sort of, our goal is to be able to actually fix model performance in a way that sort of is limited engineer effort. Okay, so I'm going to break down these sort of these data engineering techniques, and then show you sort of how that was actually used in our downstream task. Sorry. Okay, so the first one is sort of what we're calling data augmentation. And again, there's a lot more details about all these methods. I'm no expert by any means, but I'm going to give you sort of a high level overview as to what they are and how they would work in the setting. So again, we're trying to sort of fix our embedding errors. We're trying to improve our model so that it does better at predicting sports teams rather than countries. So one method is what I just said, it was augmentation. And this is where you basically apply transformations to an input example like text to generate a new training example. And so in this case, for example, if you had the sentence that Japan scored an own goal against England, you could apply a transformation there that's like, okay, if I see a national sports team, I can replace it with another national sports team. And so in this case, you could potentially generate another example, which is Italy scored an own goal against England, and train on that as well. So this is an augmentation method. It's a transformation-based method. And there's a whole bunch of theory on what this is really doing, but this is one way that you could do it. Now, a week's revision or week labeling method is one where you sort of weekly label or Or as I'll show, we do actually a relabeling technique, but you use sort of heuristic labeling functions to sort of merge different sources of supervision together to generate more training data. So if you had some sort of unlabeled sentence that was from a sports website that was talking about, Madrid's hat trick by Ronaldo won the game, you could conceivably write a labeling function that was looking for sort of popular sports, soccer players and the teams that they played on, and then weakly labeling those as mentions as well that you could train on. And this is, again, very similar to the method that we did with Wikipedia to improve performance back in Bootleg. Now, the last method is what we're calling sort of slicing or slice-based learning. I'm going to leave all the details to this paper, which also came out of sort of the Hazy lab, but it's a method for basically training an inexpensive mixture of experts. And the core principle behind this, or the core thing that needs to happen, is that you as a user sort of go through and define relevant subsets of data. And so, for example, in this use case, maybe you wanted to have a subset of data that's over sports teams, like national sports teams. And on the other hand, maybe you wanted another slice that was over sort of political entities. So for example, in this sentence, like Japan ranked 20th in the world by FIFA would be a sentence in the sports slice, whereas Greece's national debt would be one in the political slice. And then what this slice-based learning method does is it allows the model to sort of specialize on each of those slices and then learn sort of how to integrate those predictions together. And again, I'll leave the details to the paper, but what's needed here is, again, the sort of data engineering technique of understanding and defining what these relevant subsets of data are. So these three techniques, I'm going to sort of basically go through a use case that we've been sort of playing with in our lab, which is showing that you can actually sort of patch at least this entity embedding, the NED system, through one of these data methods. And so in our case, we actually take more of a weak supervision approach for this one example, although we've done experiments that show that all methods work. And in this case, we're going to actually apply a sort of weakly heuristic function to, in essence, actually correct for labels in Wikipedia, which I'm sort of counting as a weak labeling method here. And that's because Wikipedia, as it in the end of the day is labeled by users, is not always accurate. And in fact, from our sort of mining of Wikipedia, about 5% of mentions that have a very strong sport-related keyword, like the words match against, play against, are actually incorrectly labeled as countries. So for example, in Wikipedia, we found the sentence of English player Harry Kane scored a goal in their match against Germany. And in that case, we saw that the Germany was actually labeled as the country, not the sports team. And so this is also causing not only confusion to the model and mixed signals, but it's going to be what's hurting some of our NAD performance. And so we went through Wikipedia and we sort of weakly relabeled some of the data examples so that instead of Germany, the country, it was actually pointing to the national soccer team when a strong sort of sports keyword was present. And so here we sort of went through, we updated our NED system, and we found that there was about a 25 absolute accuracy improvement in disembedding these sports teams examples without actually hurting performance over the country examples. And now it is still sort of future ongoing work in our lab, which is understanding how these improvements in the entity disambiguation performance actually impacts the downstream performance as well. So again, this is very sort of preliminary ongoing results, but was something that was really exciting for us to see that just by sort of modifying the data and clicking like a train button, basically, we could change the behavior of the model. Okay. Okay, so going, so I should, please,
yes.
yes.
One question there. How did you identify that this was the subset of the training data that you needed to correct, right? So I'm not going to fight you on weak supervision being a useful technique or the broad view on. Oh, sorry, apparently Eleanor is. She loved your entity disambiguation slide. She was.
I'm sorry.
She doesn't like these ones. I'm sorry, but I like them. But I guess in my mind, the hard question is how do you know that, how do you know where to look in the data to resolve this particular error mode?
Yeah, that's actually a question that I sort of have as like a really great sort of future work. And how this was done, honestly, right now was a lot of like some manual error analysis and a little trial and error. Is we obviously, it was easy for, not easy, but we were very clearly recognized that that the issue was this sort of national sports team country error in the model, that this was something that was causing issues. And it honestly was some domain knowledge on my part that I have been dealing with Wikipedia data for a long time now, that I was sort of understood, and you can sort of do some sort of simple mining to understand that this is sort of potentially causing an error in the model. And honestly, it's not a great solution because it was a bit iterative. Like we tried a couple different methods, saw that some of them worked, some of them didn't work. And actually one sort of thing here that I have as a future problem, which I think is a huge, I don't know the right answer to this, but is doing exactly what you said, which is saying, I have an error. I need to understand what data caused that error, or what was most impactful for that error. So I know potentially what I either need to fix, correct, relabel, augment, something along those lines. Yeah, I think that's a huge issue. And I mean, my solution was not great. It was basically you hire a PhD student, which is not a solution at all.
No, I mean,
yeah.
That's how most of it. I mean, I was just curious, and I think actually Cheng Yu, who's here, was doing some looking into this exact kind of question about the latter part of the feedback loop. There's also some papers from Percy's group on influence functions that I could send, or people in the lab would know about, that talk about that, provenance back to training data points or groups of training data points. They actually had an extension that referenced labeling functions.
Yeah, no, that would be awesome. I've been looking for work in this area too. It's something that I'm working with. There's some work in our lab on basically building sort of a better evaluation toolkit, and our sort of pipe dream, which who knows if it'll ever happen or not, is to have a user sort of define a subset of data, and we like click a button and can sort of display to them like, here are the relevant data points, and like here are augmentations that could work. I mean, again, way far off work. But like in my mind, and in my mind, there's also this really interesting point, which is these embeddings kind of convolute the information. Because like, what if you get a pre-trained embedding from like Hugging Face, right? I don't actually know. I mean, okay, I know what model data was trained on there because they sort of release it all. But like, what if I don't actually know what the training data was in the first place? Can I still kind of understand what happened to the embedding and to still be able to correct it somehow? I have no idea. Maybe. But yeah, there's a lot of really very exciting questions in this space. That I have more questions than I do have answers. And so as a sort of a high level, this is sort of concluding up the talk here. I wanted to leave some time for questions. But this is really where I sort of see there as being a lot of exciting questions in terms of this data management, this ecosystem here. There's been a lot of great work in terms of like feature stores, and there's a new question here, was like, how do embeddings change that? How do they what else is needed here? I think some really interesting questions for me is like, what about embedding search? And I mean, specifically, I am building a QA model. How do I know what embedding is best for me? In particular, when I'm dealing with like memory or sort of compute constraints, where I can't just take like the biggest model that there is. We had some interesting work in our lab that was showing, they didn't even know this was going to happen, but that basically the pre-trained embedding that they use had like dramatic impact. They were doing some clustering work with sort of subclasses. And they found that the pre-trained embedding that they use actually really dramatically changed the performance depending on the end task. So there's this huge open question of like, how do you even give users some guidance as to what embedding is best for them? And so that's something that I'm very interested in. And this also notion of like sort of explaining or provenance of end result back to the training data. And especially if you're working through this embedding, there's that sort of added twist of understanding is the issue something like with locally the model, is it something back with the training data for the embedding itself? Sort of how do you help a user figure out what errors are needed to be fixed? Because right now it's very manual and not great. It's a problem. And something else is like notions of when embeddings come in and get updated, how do you sort of have this sort of continuous integration? If I have a new embedding, do I retrain my model? Do I fine tune it? Are there other methods for sort of incorporating this? This also hints at like this notion of how do I add in new embeddings or sort of personalized entities to these pipelines too, which I think is an interesting question. These are just a few things that I'm most excited about, although there's a lot of other exciting stuff to do in this space. Especially this end-to-end loop is really exciting.
I think the way you can phrase it also, if you want to like just okay, better phrasing for this, but if you want to joke around all the hype out in I mean, still I guess in academia, but also in the commercial market around feature stores, to say, these are the new feature stores that people are actually trying to figure out how to use, right?
Right, exactly. Or more like, no, I've been talking to some folks who are some folks who like built feature stores, and their next thing is like adding embeddings to feature stores is this whole new area that they don't really know how to handle yet. Like they can kind of provide them, but there's like all notions of like metrics over embeddings, like what matters here, what doesn't matter. That is a wide open space that I think people will be working a lot more on this pretty soon, is my guess. Yeah, it's like the new feature store. Interesting. So it's pretty much sort of what I've been doing the last year and a half. yeah, I would be happy again to take more questions or hear your feedback on things. This is still sort of a new area for me, some of this sort of end-to-end stuff that I've sort of been dipping my toe into as well, which has been fun.
Okay, Laurel. So let's thank Laurel. This was a very great talk, very intense. Thank you so much. So we do have time for questions. So thanks for leaving some time for questions. And while people are thinking about this, let me start with my question. So you mentioned applications downstream, but the only application that you talked about, as far as I understood, is query answering, question and answer, or query answering. What other kind of applications downstreams could there be?
Yeah, no, that's a great question, and something that I think I would love to do more of a systematic study to understand where there's lift or where there's not lift. A lot of the work I've done has obviously been sort of in textual embedding space, like word and entity embeddings mainly. And potentially there's gonna be some lift in some more in some tasks like sentiment analysis, or they call it something in industry and I can't remember what it is, like relevancy of words, something. I can't remember. It's sort of like the notion of what words are relevant for the meaning or for the question itself. So kind of related here. Now images is something I don't know a lot about, but is certainly in my mind fits in this category here. So like potentially like object detection methods or things downstream related to images, I think also would fit in this space. As I just don't know a lot about image embeddings, I don't talk a ton about them, but all of the same basic principles stand here, right? Especially like augmentations and images go really nicely together. So those kind of downstream tasks are also relevant. And yeah, I'm sure again, as I said before, this is a very open space. I think sort of the user facing products is where there's a lot of traction right now. So like a lot of the QA stuff. But that doesn't mean that there isn't other sort of downstream, some tasks that are the most that would also sort of benefit from this kind of stuff. It really is, there's actually this fundamental part here, which is because again, this embeddings, as I hinted at earlier, is really about sort of incorporating pre-trained knowledge. And this could either be private pre-trained knowledge, like global knowledge. And QA and question answering is really where it's easy to understand that you'll get lift from sort of pre-trained global knowledge. And so it's sort of the question of what are other tasks where that could be useful, or the methods there could be useful as well.
So I also have a question. So one of the areas where, or at least kind of a slightly related area to what you're doing here, is kind of the whole area of common sense reasoning for machines that kind of allow us not only to learn and have in the knowledge base kind of knowing the types of objects, the entities, etc., but starting to really reason about the properties, like that some objects, kind of move in a certain way or serve different purposes. So do you have any thoughts of going beyond kind of the entity extraction and just the relationships in the entities into more complex information that we could capture in the embeddings about these entities that you're actually learning about?
Interesting. Yeah, I haven't thought a lot about that. That's sort of interesting in terms of also I've been thinking a lot about how would those be trained as well. Yeah, so I don't have a great answer to that beyond that. That's certainly an interesting question as to what kind of features and information can you encode, and sort of what's the right way of encoding it. Because I would imagine that for some of these like properties or things that objects can do, you'd want to encode them sort of at different levels as well. But yeah, no, that's an interesting question, and I honestly haven't thought a lot about that space, but that's a good thing to take note of.
One thing I was also, oh, sorry, someone else go first.
Well, this would be my second question. So, but I'm interested in this. So the queries you showed us, and the ones I typically know are handled in query answering, are pretty simple. So they are of the type subject, predicate, object. Like Lincoln is 6 feet tall, and you are asking how tall is Lincoln? Or Paris is the capital of France, and you're asking what's the capital of France? Can you do you envision a way to extend the system to more complicated queries? And queries from databases, we can ask very complex queries, and so how far can this technology take us?
Yeah, so I mean, for me, when I think of something that's more complex, it's less about QA and more like I mean, some other sort of natural areas that this would fit, which is more complex text, which is sort of more like standard entity disambiguation I always associate with in terms of document level, right? So you're sort of resolving the entities there to let you do sort of document search or document summarization. So at least that's also one, now that I thought about it, sort of another sort of downstream task where this is useful. Yeah, no, you're right that those are sort of somewhat I feel like the paper that I'm thinking in my head, which I'm not sure actually, is sort of some of that work that they've done sort of neural databases, right? Which is sort of understanding what are sort of the limitations of like QA models to answering queries. Yeah, that's interesting work. I'm not sure where that's going to go yet, but yeah. So I can't. I mean, I don't know where the limitations are in terms of what where the QA models, like where their limitations are. For me, I'm more always interested in what are the limits of like when is sort of entity knowledge going to be helpful to you, and when is it going to be less helpful? So that wasn't exactly answering your question. But yeah, I guess that's I was more I've been more thinking on the terms of when is this entity knowledge useful in sort of what are more complex situations where that is potentially necessary. We have some work also going on in terms of medical stuff, which is really interesting, very hard. So I know nothing.
Thanks, it makes sense. So Alex, please, I interrupted you.
Oh, I was just going to ask, how do you think about? I feel like I'm stealing this question from someone because I'm just asking a dumb one about connection to the subject of the reading group that I didn't lead last quarter around, embeddings of, structured data, I don't know, structured knowledge or structured, yeah, I mean, so relational data. Sorry, I'm a little rattled. I'm curious. Here, you're learning embeddings over relational data, and there's a bunch of work over of kind of learning embeddings over relational databases, stuff like that. In this case, you have this structured data that's also got unstructured text, and you're trying to learn the embeddings by training for a specific predictive task. In these other kind of learn embeddings for relational data, you're trying to essentially do the like kind of leave one out type approaches of
right, like
learn
the
trans-E,
multi, all the big E ones, yeah.
I'm kind of stumbling through. Clearly, sorry, it was a long day. Making this comparison in terms of, okay, there's obviously a difference in that here you have structured data, but it's also got unstructured text, and you're training for a specific predictive task.
Right,
so
right.
For leaving a specific column out, which is namely the entity disambiguation.
Right.
In these other methods, you're just kind of only over structured data, and you're leaving a variety of other kind of entries out to form the predictive task. But any thoughts about how to think about how these two relate beyond what I stumbled through there? or correcting what I stumbled through there? That's
actually really, I haven't actually thought about NED in that sort of sense before. So I mean, the thing that pops in my mind, which maybe not obviously the right thing to think about at all, is there was a recent work that was shared that I honestly don't understand the theory of it all, but they were explaining how you could really reform most sort of downstream language tasks as a next token prediction. And this was their attempt to understand and explain why these like sort of masked language models or sort of next token models were so helpful in downstream tasks. It kind of doesn't make a lot of sense, right? It's trained on like one task and it's useful for downstream tasks. And so there's something here where I do think there's some sort of unifying something in terms of what everything can, I mean, not everything, but I think a lot of things maybe is what you're getting at here is can be reformed as like a next token prediction, right? Because that's in essence what all that the trans-E stuff was like, okay, what's the next link here? And this is in essence the same idea as like what's the next entity. So yeah, maybe there is some sort of fundamental thing, which is like all that these models are really doing at their core is like a next something, or like predicting the missing piece. Which goes to something that Chris was talking about today, which is like how, is there any way that we could make everything just be an NLP layer? Future dreamings, I think. So yeah, that's sort of, you answered a stumbled question. I gave you a stumbled answer of sort of potentially something that at least came to my mind when you mentioned that of there might be some, unifying sort of core principle here about what these models are all really doing at the under the hood.
No, that was great. And I'm sorry, I gave not only a stumbled answer, but also it was, stumbled question, but it was also barely a question because I was more just kind of saying that it's,
yeah. No, you're right. There is some sort of fundamental something here.
Yeah, or rather, broadly, there's been some, recent work, like we had a reading group last quarter on this around, how can we embed, structural knowledge, and there's a lot of attention in the ML community. How can we embed, basically the same thing, graphic, how can we embed graphs? And this seems to be a version of this.
Well, did you guys look at like the star embeddings at all from Facebook, where they are like, screw all this different embeddings, we're just gonna throw everything in the same embedding space, and sort of at least from what I understood, they were like, if the differences don't matter, we're all gonna do it all together. I can't remember how they actually trained them, but that was sort of an interesting idea. I'm not quite sure if it's the right answer, but it was sort of interesting that they're doing that.
Yeah, again, mine was even, I don't know, maybe interesting barely qualifies as a question. I'm more just musing. It's interesting to think about all the different kind of design choices here, like the fact that, in that case, yeah, like that paper and some others, like in the graph literature, they just throw everything in the same space. Here you had, 3 distinct spaces for 3 distinct, types of features or relations. In some of those settings, it's purely the kind of like predict the next token or predict the next, link or hop in the graph. Here it is, predicting a very specific label, instead, and just, I don't know. So I more just think it's interesting to understand how these all kind of go together, because it's clearly there's a lot of excitement in the space, but clearly there's some very fundamental things that kind of tie together.
Yeah.
Like if you can embed structural knowledge, you will do better.
Right. No, yeah, you're totally right. It's an exciting space, and it's sort of interesting to be seen, especially some of the recent papers. I think there's one in Sigmod last year, which was like, they're all trying to answer kind of how do I embed like a database, right? How do I embed a relation? Not so much a huge knowledge graph, but I think it's a really interesting question that people are sort of stumbling around trying to find the right answer. And I don't know what it is, but it's sort of interesting to see what happens.
Okay, so we are running out of time. So Laurel, thanks a lot for joining today and preparing and giving this great talk. We are recording and we are going to post the video online. And yeah, thanks everyone for coming, and I'll see you all next week.
Also, thank you so much, guys.
Thank you.
Bye-bye.
Bye-bye.
Bye.